Electrochemistry. What is a galvanic cell and introduction? Whenever a redox reaction is allowed to take place in a single beaker, it is found that the solution becomes hot. For example, when a zinc rod is placed in copper sulfate solution, the solution is found to be warmer and the reaction proceeds according to the equation. Zinc plus copper sulfate gives zinc sulfate plus copper. Similar results are observed when a rod of copper is placed in silver nitrate solution. Thus, we conclude that whenever a redox reaction takes place in a single beaker, chemical energy in the form of heat is produced. By suitable means, it is possible to convert chemical energy into electrical energy. A device used to convert the chemical energy produced in a redox reaction into electrical energy is called galvanic cell or voltaic cell after the names of Luigi Galvani or Alessandro Volta, who were the first to perform experiments on the conversion of chemical energy into electrical energy. How a redox reaction can be used to produce electrical energy leading to the formation of a galvanic cell can be understood by taking the above two examples of redox reactions again. First, redox reaction between zinc and copper sulfate. This reaction is zinc plus copper sulfate gives zinc sulfate plus copper. It may be written as zinc plus copper ions gives zinc ions plus copper. The reaction may be split into two half reactions as under zinc gives zinc ions plus 2 electrons, which is oxidation half reaction, and copper ions plus 2 electron gives copper, which is the reduction half reaction. The first reaction is called the oxidation half reaction and the second is called the reduction half reaction. The reaction obtained by adding the two half reactions is called the overall reaction. Thus, if a redox reaction is allowed to take place in such a way that oxidation half reaction takes place in one beaker and the reduction half reaction in the other beaker, the electrons given out by the former will be taken up by the latter and a current will flow. This is achieved as follows. A zinc rod is placed in zinc sulfate solution taken in beaker. A copper rod is placed in copper sulfate solution taken in another beaker. The two rods are connected by a wire and the two solutions are connected by a salt bridge. A salt bridge is a U-shaped tube containing concentrated solution of an electrolyte like KCl, KNO3, K2SO4, etc. or solidified solution of such an electrolyte in agar-agar and gelatin. The function of salt bridge is to allow the movement of ions from one solution to the other without mixing of the two solutions. Thus, whereas electrons flow in the outer circuit in the wire, the inner circuit is completely by the flow of ions from one solution to the other through the salt bridge. Some important features of the above cell may be summed up as follows. First, the zinc electrode at which oxidation takes place is called the anode. The copper electrode at which the reduction takes place is called the cathode. Second, since electrons are produced at the zinc electrode, it is designated as the negative pole. The other electrode, example the copper electrode, acts as the positive pole. Third, the electrons flow from the negative pole to the positive pole in the external circuit. However, conventionally this current is said to flow in the opposite direction. Fourth, the oxidation of zinc into zinc ions produces excess of zinc ions into the left beaker. Similarly, the reduction of copper ions into copper atoms leaves the excess sulfate ions in the solution in the right beaker. To maintain electrical neutrality of the solutions in the two beakers, the cations and anions move through the salt bridge. This helps to complete the inner circuit as already mentioned. Fifth, as copper from copper sulfate solution is deposited on the copper electrode and sulfate ions migrate to the other side, the concentration of copper sulfate solution decreases as the cell operates. Consequently, the current falls with the passage of time. Evidently, the weight of copper rod will increase while that of zinc rod will decrease as the cell works. The cell based on the above reaction is commonly called Daniell cell. A popular form of this cell is shown in figure 6.3. Here salt bridge is replaced by a porous pot through which the sulfate ions migrate from copper sulfate solution to the zinc sulfate solution. is a redox reaction between copper and the silver nitrate solution. The reaction is copper plus 2 moles of silver nitrate gives copper nitrate plus 2 moles of silver, or it may be written as copper plus 2 moles of silver ions gives copper ions plus 2 moles of silver. The two half reactions will be copper gives copper ions plus electrons, which is oxidation half reaction, and silver ions plus electron gives the silver, which is reduction half reaction. Here oxidation takes place at the copper electrode, therefore it acts as anode or negative pole. Reduction takes place at the silver electrode, it acts as cathode or positive pole. The flow of conventional current is from silver to copper. In a similar manner, based upon any redox reaction, a Ganwell cell can be constructed. What is an electrolytic cell? If the aqueous solution of electrolyte or the molten electrolyte is taken in a vessel and two metal rods are immersed into it and then connected to a battery, the ions start migrating towards the electrode. The cations, positive ions towards the cathode connected to the negative of the battery, and anions, negative ions towards the anode connected to the positive battery. The anions on reaching the anode loses electrons, example oxidation takes place. The cations on reaching the cathode gain electrons, example reduction takes place. Thus, at anode, anion gives atom plus electron, which is oxidation, and at cathode, ion plus electron gives atom, which is reduction. Thus, the redox reaction takes place on supplying electrical energy resulting into the decomposition of the substance. Such an arrangement in which electrical energy is applied to bring about the redox reaction, which is otherwise non-spontaneous. Example, to bring about the decomposition of the electrolyte, a phenomenon called electrolysis called an electrolytic cell. Difference between galvanic cell and electrolytic cell. The main points of difference between the galvanic cell and electrolytic cell may be summed up as follows. Point of difference between galvanic cell and electrolytic cell. Galvanic cell is a device to convert chemical energy into electrical energy. Example, electrical energy is produced as a result of the redox reaction taking place. Whereas electrolytic cell is a device to convert electrical energy into chemical energy. Example, electrical energy is applied to the electrolytic solution to bring about the redox reaction. Example, electrolytic. Second, galvanic cell is based upon redox reaction which is spontaneous, and the electrolytic cell is and in electrolytic cell the redox reaction is non-spontaneous and takes place only when electrical energy is applied. Third, in galvanic cell, the two electrodes may be set up in solution of the same or different electrolytes. The former are called concentration cells, whereas in electrolytic cell, the two electrodes are set up in the same electrolytic solution. Fourth, in galvanic cell, electrode on which oxidation takes place is called the anode or negative pole, and the electrode on which reduction takes place is called the cathode or positive pole. Whereas in electrolytic cell, the electrode which is connected to the negative terminal of the battery is called the cathode. The cations migrate to it when it gain electron and hence reduction takes place here. The other electrode is called the anode. In galvanic cell, to set up the cell, a salt bridge or a porous pot is used, whereas in electrolytic cell, no salt bridge is used in this case. Remember that galvanic cells and electrolytic cells are collectively called as electrochemical cells because in the former chemical energy of a redox reaction is converted into electrical energy, whereas the latter converts electrical energy into chemical energy. Representation of a galvanic cell. A galvanic cell is represented in a manner as illustrated below for the Daniell cell. Zinc is in contact with zinc ions having salt bridge in between, where the zinc copper ions is in contact with copper. Example, by convention, the electrode on which oxidation takes place is written on the left hand side and the other electrode on which reduction takes place is written on the right hand side. The electrode on the left hand side is written by writing the symbol of the metal, first followed by the symbol of the ion with its concentration in brackets. The electrode on the right hand side is written by first writing the ion along with its concentration in brackets followed by the symbol of the metal. Single vertical line represents the phase boundaries of the electrodes and the double line represents the salt bridge. C1 and C2 represent the concentration of zinc ions and copper ions respectively. In a similar manner, copper silver cell may be represented as copper in phase boundary with copper ions in contact with the solid bridge and silver ions in contact with silver. Electrode potential. In a cell, oxidation takes place at one electrode and reduction at the other. In other words, one electrode has the tendency to lose electrons while the other has the tendency to gain electrons. The tendency of an electrode to lose or gain electrons when it is in contact with its own ion in the solution is called its electrode potential. The electrode potential is further termed as oxidation potential if oxidation takes place at the electrode with respect to normal hydrogen electrode, and it's called reduction potential if reduction takes place at the electrode with respect to normal hydrogen electrode. Further, if in the half cell the metal rod is suspended in a solution of unit activity or 1 molar concentration, assuming the solution to be ideal and the temperature is kept at 25 degrees Celsius, the electrode potential is called standard electrode potential, represented usually by E naught. If a gas is involved, the standard conditions chosen are 1 atmosphere pressure and 25 degrees Celsius. EMF of cell and its measurement. The force which causes the flow of electrons from one electrode to the other and thus results in the flow of current is called electromotive force, usually represented by EMF and measured in volts. This force evidently arises because of the different electrode potential possessed by the two electrodes. This electromotive force may also be defined as the difference of potentials which causes the current to flow from an electrode at a higher potential to an electrode at a lower potential. If all the reactants and products are present in their standard state at 25 degrees Celsius, the EMF is called standard EMF. To measure the EMF of cell, the easiest way is to connect the two electrodes to a voltmeter. The potential difference, for example the voltage, can be read directly from the voltmeter. However, such a measurement suffers from the following two serious objections. First, the voltmeter draws some current from the cell, thereby changing the EMF of the cell. Second, with appreciable flow of current, a part of the EMF will be utilized to overcome the internal resistance of the cell. To overcome the above objection, potentiometric method, which is based upon Poison-Draw compensation principle, is used for the accurate measurement of EMF. In this method, the unknown EMF is opposed by another known EMF until the two are equal. The general principle involved may be explained with the help of figure 6.6. AB is construct is a stretched wire of uniform thickness. As is the standard cell whose EMF is known, it is connected to the ends A and B. X is a cell whose EMF is to be determined. One end of the X is connected to the end A and the other of the sliding contact J through the galvanometer J in such a manner that it sends EMF in a direction opposite to that of the cell. As the sliding contact is moved along the wire AB, till at a particular point, say C. No deflection is observed in the galvanometer. If ES represents the EMF of the standard cell S and EX that of the experimental cell X, then obviously ES directly proportional to length AB, EX directly proportional to length AC. Therefore, EX by ES is equal to length AC upon length AB. Therefore, EX is equal to length AC upon length AB into ES. Thus, knowing ES and EX can be calculated. Alternatively, knowing the value of ES, the wire AC may be calibrated in volts to give the reading EX directly. The above method gives a great result only if the following conditions are satisfied. First, ES should be greater than EX. Second, the wire AB should be uniform. Third, the galvanometer should be highly sensitive. Alternatively, the following arrangement may be used. A cell S test or a storage battery of voltage greater than that of the standard cell S of the or that of the experimental cell X is connected to the ends A and B of the test uniform wire AB through the variable resistance R. The sliding contact is fixed at the point C. Key is inserted at A so that the standard cell S is in the circuit. The variable resistance R is adjusted till there is no deflection the galvanometer G. If ES is the EMF of the standard cell, then obviously ES is directly proportional to length AC dash. Now the key is removed from position A and inserted in position B so that the experimental cell axis in the circuit. The sliding contact J is moved along the wire AB till no deflection is observed in the galvanometer. Let us suppose that it occurs at the point C. Then if EX is the unknown EMF, we have EX directly proportional to length AC. Therefore, EX upon ES is equal to length AC upon length AC dash, or EX is equal to length AC upon length AC dash into EF. Thus, knowing EX can be calculated. Standard cell. A standard cell is a cell which fulfills the following requirements. First, it has a constant value of EMF which is reproducible. Second, the EMF does not change with the passage of time. Third, the temperature coefficient of EMF is very low. The best known cell which meets the upper requirements approximately is Weston standard cell, the usual form of which is shown in figure 6.10. It consists of an H-shaped glass vessel. One of the limbs contains mercury covered with a paste of mercurous sulfate and mercury. This limb acts as the anode. The other limb, which acts as the cathode, contains cadmium amalgam covered with the crystals of cadmium sulfate into 8 by 3 moles of water, and then saturated cadmium sulfate solution. Short platinum wires are sealed into the bottoms of the limbs to make contact with the active materials. The rims are finally closed with cords and sealing wax. The purpose of placing solid crystals of cadmium sulfate into 8 by 3 moles of water is to keep the cadmium sulfate solution saturated at all temperatures. The EMF of the above cell is 1.0185 volt at 15 degrees Celsius and 1.0181 volt at 225 degrees Celsius. The reaction taking place in the cell is as follows. Cadmium plus mercurous sulfate plus aqueous gives cadmium sulfate into 8 by 3 moles of water plus 2 moles of mercury. The cell is reversible in the sense discussed in the next section. Reversible and irreversible cell. In thermodynamics, a reversible process is defined as a process in which first the driving force is infinitesimally different from the opposing force, and second the process can be reversed by applying force infinitesimally greater than the force already acted. The concept of reversible process is highly significant in thermodynamics because a number of relationships have been derived for the processes that are thermodynamically reversible. In a cell, chemical energy is converted into electrical energy. In order that the thermodynamic relations may be applicable to cells, the cell must operate under reversible conditions. A cell is said to be reversible if it satisfies the following three conditions. If an opposing EMF equal to that of the cell is applied to the cell, no current should flow in the circuit and hence no chemical reaction should take place. Second, if an opposing EMF slightly smaller than that of the cell is applied, an infinitesimally small current should flow from the cell and infinitesimally small reaction should take place. Third, if an opposing EMF infinitesimally greater than that of the cell is applied, an infinitesimally small current should flow in the opposite direction, and an infinitesimally small reaction in the reverse direction should occur. If the above conditions are not satisfied, the cell is said to be irreversible. A well-known example of a reversible cell is that of Navier cell, consisting of a zinc electrode dipped in a zinc sulfate solution and a copper electrode dipped in copper sulfate solution. When it is producing current, the reaction taking place in the cell is zinc plus copper ions gives zinc ions plus copper. When an opposing EMF equal to that of the cell is applied, the reaction stops completely and no current flows at all. When an opposing EMF infinitesimally smaller than that of the cell is applied, an infinitesimally small current flows from the cell and the above reaction is found to take place. If opposing EMF infinitesimally greater than that of the cell is applied, an infinitesimally small current flows in the opposite direction and the opposite reaction is found to take place in the reverse direction. In the potentiometric method for the determination of EMF, As no current flows at the time of measurement, the conditions of reversibility is satisfied. Now let us consider the example of a cell which is irreversible. Consider a cell consisting of a zinc rod and a silver rod dipped in dilute sulfuric acid. When the two rods are connected with a wire, the following reaction takes place. Zinc plus hydrogen sulfide gives zinc sulfide plus hydrogen. Example, zinc is oxidized to zinc ions and hydrogen is ions are reduced to hydrogen gas. In other words, zinc dissolves at one electrode and hydrogen gas is evolved at the other. Now the cell is connected to an external source of EMF, say a battery, whose EMF is slightly greater than that of the cell and is opposing to the cell. Silver dissolves at one electrode and hydrogen gas is evolved at the other. That is, silver plus hydrogen sulfide gives silver sulfide plus hydrogen. Example now, oxidation takes place at the silver electrode and reduction at the other. Thus, though the above cell can be made to satisfy the first condition of reversibility. Example, the direction of the current can be reversed by making the opposing force infinitesimally greater than the driving force. The second condition of reversibility is not satisfied. Example, the chemical change is not reversed. Instead, a new chemical reaction takes place. Hence, the opposite cell is not reversible but is reversible. Such cells, however, do not have any thermodynamic significance. Reversible electrodes. Two electrodes of a reversible cell are called reversible electrodes. Each electrode is termed as reversible electrode because the half-cell reaction occurring at the electrode can take place in the direction as well as in the reverse direction. The various reversible electrodes are classified into the following 5 different types. First, metal-metal ion electrodes. Such an electrode consists of a metal dipped in the solution of its ions. Example, zinc rod dipped in zinc sulfate solution, copper rod dipped in copper sulfate solution, etc. Taking the example of copper-copper ion electrode, when oxidation takes place at the electrode, the reaction may be represented as copper gives copper ions plus 2 moles of electrode. On the other hand, when reduction takes place at the electrode, the reaction may be represented as copper ions plus 2 electron gives copper. Thus, the electrode is reversible with respect to copper ions. Second, amalgam electrode. These electrodes are just like metal ion electrode except that the metal is replaced by its amalgam. Example, solution of the metal in mercury. For example, zinc amalgam electrode consists of zinc amalgam dipping into a solution of zinc ions. The electrode is thus represented by zinc amalgam in contact with zinc ions. When oxidation takes place at the electrode reaction is zinc amalgam converted into zinc ions plus 2 moles of electron. When reduction takes place at the reverse reaction is written. Example, zinc ions plus 2 electron gives zinc amalgam. Thus, the electrode is reversible with respect to zinc ions. Amalgam electrodes are preferred over metal-metal ion electrode for the following reasons. First, equilibrium between the amalgam and the ions is established more quickly than with the pure metal. Second, active metals like sodium, potassium, calcium, etc. cannot be used directly as electrodes in aqueous solution. However, by changing them into amalgams, their activity is reduced. They can be used. Third, the impurities present in metals which sometimes cause erratic behavior in pure metals are diluted by amalgamation to give satisfactory results. Gas electrode. These electrodes consist of a gas bubble around an inert metal wire or foil, usually of platinized platinum, immersed in the solution capable of furnishing the ions of the gas. The functions of the metal wire or the foil is that firstly it helps to establish the equilibrium between the gas and its ions, and secondly it helps to make an electrical contact with or electric lost or gained can flow through it. A few common gas electrodes are briefly described below. Hydrogen electrode. The design of a hydrogen electrode, which is in fact the general design for any gas electrode, is shown in figure 6.110. In the standard or normal hydrogen electrode, hydrogen gas at 1 atmospheric pressure is passed into 1 molar HCl acid in which the foil of platinized platinum remains immersed. When a cell, this electrode acts as the anode. Example, oxidation takes place. The following reaction takes place. Hydrogen gas gives ions plus 2 moles of electron. Example, some hydrogen gas changes into hydrogen ions which go into the solution. When this electrode acts as cathode, example, reduction takes place, the following reaction occurs. 2 moles of hydrogen ions plus 2 moles of electron gives hydrogen gas. But some hydrogen ions from the solution change into hydrogen gas. Thus, the electrode is reversible with respect to hydrogen ions. This electrode is usually represented as PtS2, platinum hydrogen gas in contact with hydrogen ions. Second, chlorine electrode. In this case, chlorine gas at a given pressure is passed into hydrochloric acid, which is capable of furnishing the chloride ions. For oxidation to take place, the following reaction occurs. 2 moles of chlorine ions gives chlorine gas plus 2 moles of electron. For reduction to occur, the following reaction takes place. Chlorine gas plus 2 moles of electron gives chlorine ions. Third, oxidation electrode. This electrode is reversible with respect to hydroxyl ions. Thus, to construct this electrode, oxidation gas at a given pressure is passed into solution capable of giving OH negative ions. For reduction to occur, the reaction taking place is oxygen plus 2 moles of water plus 2 moles of electron gives 4 moles of hydroxide ion. For oxidation to occur, the reverse reaction takes place. Fourth, metal insoluble salt and ion electrode. This is most commonly employed category of electrodes. Here the electrode consists of a metal in contact with its sparingly soluble salt and a solution of a soluble salt containing the same ion as that of the sparingly soluble salt. A few examples of the electrode of this type are silver chloride and potassium chloride electrode, prepared by dipping a silver wire in KCl solution to which a drop of AgNO3 is added to form AgCl. Second, PbSO4, PbPbSO4, K2SO4 electrode, preparing by dipping lead wire in K2SO4 solution to which a few drops of lead nitrate solution are added. Third one, mercurous chloride, potassium chloride electrode, which is also known as calomel electrode. This is the most frequently used electrode. It is prepared as follows. Pure mercury is placed at the bottom of a tube T. It is covered with the base of mercurous chloride, calomel, and then filled with the either normal or saturated solution of KCl from the side tube A such that the side tube B is also filled with the KCl solution. A tube C having a piece of platinum wire sealed at its end is fixed into the tube T such that the platinum wire remains dipped into the mercury. A little mercury is placed in the tube C and a copper wire put into it to make an electrical contact. An alternative form of the calomel electrode used very frequently in the library as one. Oxidation cannot occur at this electrode. 2 moles of mercury gives mercurous ions plus 2 moles of electron, and mercurous ions plus 2 moles of chlorine ions gives mercurous chloride. Therefore, 2 moles of mercury plus 2 moles of chlorine ions gives mercurous chloride plus 2 moles of electron, which is the overall reaction. The reduction can occur at this electrode in a reversible manner. The overall reaction is just the reverse of the overall reaction when oxidation takes place. Hence, the calomel is reversed with respect to chloride ions. Oxidation reduction electrodes. These electrodes are prepared by dipping a platinum wire into the solution of two salts of the same metal, different valences. Example, ferrous and ferric salts, stannous and stannic salts, or ferrous and ferric salts, etc. The EMF rises because of the tendency of the metal ion in one oxidation state to pass into the second more oxidable state. The function of the platinum wire is merely to pick up the electrons and to make an electrical contact. electrode. The reaction taking place in such an electrode may be represented as Fe2 positive gives Fe3 positive plus electron, Sn2 positive gives Sn4 positive plus 2 electron, Ce2 positive gives Ce3 positive plus electron.